right. Let's see. The one thing that I want to do today is some Python, but before I do the Python, I just want to scribble a little bit because well, remind you what we are going to be solving. All right, so we are going to solve a 2D heat transfer problem. And it's going to be this P-mesh that you have used for your so 2D heat transfer problem. And we're going to have this P-mesh that you have seen, for which we're doing some plotting. And we're going to solve I don't want to have fluxes because I haven't told you how to find those boundaries. So we're definitely going to do a source term and then pick a source term. I don't know, any function of X and Y or a constant. I don't care. What do you want? We'll change it. There's something on the PL5 that is already up, but we can change it to keep it interesting. No. Your favorite function? Anyone? No favorite functions? Let's do something like X plus Y, something linear. Then we actually do need to integrate it, which I don't. Well, let's do two options. Let's do option. First, I'll do it with a constant because then I don't need to rederive anything. Let's just do 5. I don't know what that is. We need to pick a K. I have no idea. There's probably some K value for the conductivity. Just pick one randomly. I think that's all I need. And then we need some boundary condition. So we are going to put a boundary condition on the bottom. So here we're going to fix the temperature. And then, yeah, you can decide what temperature, any value for the temperature. Okay, 5. Let's do 5. All right, so we're going to solve this problem. And what will we need to do to solve this problem? At the end of the day, we will get this big K matrix, the T, and then that equals plus the force vector equals 0. There is, yes. And this force vector, we also know how to calculate. This is basically the one, then this is what you are doing for your homework. We're gonna do it for the triangles. So we have to calculate the stiffness matrix and the force vector. We have to be a little bit careful with the signs, whether or not there's a plus or a minus sign here. And this, you can go back to the book. I'll do it myself here, but you have to be a little bit careful with the notation, because the Q, this one has the minus the gradient of the temperature. If I put a plus sign here, then when I do the integration by parts, then this one will end up with a positive. So this one will end up being this. And this one will retain the positive sign. So for this, if I have a plus sign here, I end up with, this is K times T, this one will end up being the force vector. So in my case, I will retain the plus sign. So just double checking. And the flux will have a negative sign, but I won't have any flux terms today. All right, so let's do that problem. I just need to remember S equals 5, T equals 5 at the bottom, and the conductivity equals 1. Let me stop sharing here. And let's go here. And the one thing that I need to see is, can you check if I uploaded the PMesh ordered? I know that in the original PL5, I had only PMesh, but that one does not have the nodes with essential boundary condition at the beginning. So I created another mesh, but I don't know if I uploaded it. So Python Lab 5 loads PMesh. So in the...
No, you only upload
Let me upload that very quickly then. Okay, give me 1 sec, I'll upload that. So I just changed that to... See? So the thing is that in the original Python Lab 5, I did not actually solve any problem. I just computed the stiffness matrix. But I do want to solve a problem. So let's actually solve a problem. Come on. One sec. Python Lab 5. Load files. PMesh order. There we go. All right, I just uploaded. Please download PMesh order, because that one I changed such that which one is not Google Chrome? So many windows, huh? Which one is the one that I'm supposed to be sharing? Oh, this one. All right. So load PMesh order, and then also change, I made a mistake as well. So change to -1 here. This is just for when I ordered the mesh, I did not have the indexing from 0. I had the indexing from 1. So I need to subtract 1 from all the known numbers so that they start from 0. So if you do those 2 changes, PMesh order and then subtract -1 here, then it should load. It has 727 nodes and 1,300 elements. And then hopefully this works. And this should be such that the first 51 nodes should have essential boundary condition less than 51. Let's see, 1, 2, 3, 4, 5, 6, 7. I think the first 19 nodes should have should be the. We can check 0 to 15. Then color equals red, size equals 20, something like that. Is it not like that? There we go. Yeah, so the first 15 nodes, I guess maybe I'll make it even bigger. So you can see that the first 15, if you do this scatter of the first 15 nodes, then they are the ones at the bottom. So those are the ones for which we are going to put the essential boundary condition. Yes? I'll go. Did you make the 2 changes? I'll go around. Does it work? Is that the image order? Is that the order mesh?
This is just what was separate.
Oh, can you load the order image order? The other one? Yeah. Yeah, read it, then change the file layer. Yes, that's correct. Yes. So then you can just trust this. I have already coded the shape functions and the gradients of the shape functions, so you don't have to worry about that. The shape functions take y and all, and then the gradients do not take xy because they are constant. So if you actually take the derivative, then they are constant, so no need to pass xy. Technically, they are functions of xy, it's just that they are constant. So I just, I don't pass them. But you could have xy, it's just that it wouldn't be used. And then the function to calculate the area of the element. Now, this is all done. I wish that you didn't look at that. Don't look at that. And then I'll code it from scratch. But because I want to reinforce sort of the knowledge from the class, but you can check against the code below. But basically, we need to assemble the big stiffness matrix and the big force vector. That's all our goal is, to assemble stiffness matrix and force vector. That's what we want to do. What is the size of the stiffness matrix? The big one. Look at the solution. What should be the size of the big stiffness matrix? No. Yes.
The number of nodes.
Yes, the number of nodes by the number of nodes. Whereas the force vector is just the number of nodes. So we're going to initialize them with zeros. Then to fill these stiffness matrices and force vectors, we need to compute the element stiffness matrix and element force vectors. So that means that we need to do it for all elements. So there should be a for loop. And this for loop is over the elements. Because we need to, for every element, we need to compute stiffness Fe and force Fe. Now, to compute the stiffness matrix, if you remember what the stiffness matrix is, down in the code is the same, but I'll just type it so that we're on the same page. At the end of the day, what we will compute is we're gonna compute Ke, and Ke is a matrix that has the integral of, I'll comment it here. Right, so this is integral of gradient 1 dotted with gradient 1 times K. That's the first entry. Then there's another integral that has K, and then gradient 1 times gradient 2, and so on. Now, if you recall what I was saying on Wednesday, is that even Monday, I think, and this is what you are doing for your class, for your homework. The gradients are constant. So the K is a constant. The gradients of for the linear elements are constant. So everything will go out of the integral as a constant. And then the integral is just the area, right? So at the end of the day, this will just be the area of the element times the K times an array that will only have the dot product of the gradients. So this one will just have gradient of n1 dot gradient of n1, then gradient of n1 dot gradient of n2, and so on. And it's going to be a 3 by 3 because there's 9 combinations for those dot products. But again, this all comes from when we went from the weak form and we plugged in the discretization, what we ended up was with K gradient n1 dotted gradient, well, gradient ni, gradient nj, and there are 9 combinations, which are those. But for the linear element, you can just take everything out of the integral, and then you're left with just the area of the element, and then just the dot product of the gradients. So that's what we need to do. So we need to compute the gradients. For that, we have to just call our function. I'm gonna work backwards. But basically, we need to compute these different gradients, right? I still haven't found what x1, y1, x2, y2, and x3, y3 are, but I need to call those functions. Once I call those functions, I also need to calculate the area of the element, so I can just call my function. This will give me the area of the element. And we said conductivity equals 1. Therefore, the stiffness matrix is just MP dot. And then the first one, like I said, is gradient 1, gradient 1. Then the second one, you just need to fill this out. This one is this. The third one is like this. So this is the first row. And the second row is I think I have an extra. There we go. Second row is just N2, N2, 2. The third row is just N3, 3. So again, this well, and then times the area times the K. So the conductivity times the area times the matrix that just has the dot product of the gradients. But again, this comes from the definition of the stiffness matrix, which was the integral of the conductivity times the dot product of the gradients. For the linear triangular element, everything is constant, so the integral just gives you the area. And then the matrix is just the different dot products of the gradients of the shape functions. Now, the one thing that I have not yet gotten is what are these x1, y1, x2, y2, x3, y3. Those are the nodal coordinates of the element. So those I still need to go get, right? Where do I get those from? Maybe I'll give you 5 minutes to try to tell me how do I get this? Don't look at the code below. Well, maybe try for 3 minutes and then after that, then look at the code below so you can do it. But I'll go around and I'll answer questions. Random. Great. I know you.
Oh.
Sebastian, you're working. You are looking at the code from before. All right, I see some of you are looking at the code that is below. But basically, where are x and y coordinates? They all are stored in the node x. So this definitely needs to read something from the node x. Every one of these needs to read something from the node x. All the x coordinates are in the 0 column, or the y coordinates are in the 1 column. And then the question is, what node should I read, right? So if you look at the code below, this is the first node of the element, but I don't know what that is. So I'm just gonna denote it as N1, but I need to figure that out. I'm just tracing my problem down below. But the main idea is these are XY coordinates. They are all stored in the node X array. So I definitely need to go read them from the node X array. Now, what rows of that node X array should I be accessing? That depends on the element. So for every element, which rows I need to, for an element, which rows do I need to go read from the node X array? So that is basically containing the element array. So the first node of the element is, for that element, the 0 entry. That element array is what has the array that has the node numbers that make up this element. This is the same as in 1D. It's just that for your code of homework 3, you had something very similar, but in the homework 3, you probably only had 2 because every element only had 2 nodes. For this one, every element has 3 nodes. So you just go and read the 3 nodes that make up the element. But it's the same idea as in 1D. And the nodal coordinates is same code as 1D, but now read X and Y coordinates instead of just X. So in the 1D code that you had for homework 3, you were doing something like that. X equals node X and 1. The only difference is that in the homework 3, the 1D code, you were only reading X coordinates. Now we have X and Y. All right, so given the known numbers, given the XY coordinates, evaluate the gradients, and then compute the stiffness matrix. That's it. That's it for the stiffness matrix. We still need to assemble it. But let's do the force vector, then we assemble. So for the force vector, again, well, let me comment it first. What is the force vector? The force vector is the integral of the shape function 1 times the source term, and then integral of shape function 2 times the source term, and then integral of shape function 3 times the source term. And then we need to do the integrals. The source term in this case is constant. So this is just S times, and this is the solution of the other problem of the homework. which is what are the integrals of the shape functions. You can do the integral, or you can just do the geometric argument that I was telling you on Monday and Wednesday. What is the integral of the shape function over the triangle? It's nothing but the volume of that little cube, which is just 1 times 1/3 times the base, which is the area, times the height, which is 1. So just 1/3 times the area. So this ends up just being that. So then the force vector is just MP array, well, A times S, so AE times S times MP array, 1/3, 1/3, 1/3. And then S is 5, because that's what Sam told us. Questions? All right, so now the assembly. Again, it's below, I'll let you do it, but now here, I need you to tell me for every one of these entries of, so the 0, 0 entry, 0, 1 entry, the 1, 0 entry, well, I still need 0, 2 entry, there's 9 of these. Where do they go to? Give you maybe 1 minute to tell me what this should be. Maybe 2 minutes, 2 minutes. Don't look at the code below. Let's say that the element is made up of 4, 5, and 11. Then where does the first entry go? Yes, 4, 4, 4. So the 0, 0 entry goes to 4. But what is it? Because this will change for everything. Another element is another element made up of the first entry will go to. Where is that on the 4? Well, it changes per element. So it's something that I'm waiting that it's stored the element array, but I'm already waiting. Yes. N1 is the variable that has that. So I give an element and 4, therefore the next element is the change the N1. So this Waiting.
I was in the lab. I couldn't change my schedule after the spring break.
All right. So this, if you think about where the 0, 0 entry of the matrix goes, if you think about how I draw it when I do the assembly by hand, I put the known numbers as the rows and the columns of the K, and that's where it should go. So for a given element, if an element is made out of nodes, 4, 5, and 7, then the 0, 0 entry actually goes to 4, 4. And then the other one was to 4,7 and so on. So these are the known numbers. And again, this should be similar to what you have in your 1D code. So in your 1D code, this is actually the same. It's just that now you have 3 nodes. But if you look at your code from, do I call it with 0 or with 1? Okay, so I have 1. And 1 and 1. And 1 and 2. And 1 and 3. Then and 2 and 1. And 2, 2. 2 and 3. And 3 and 1. 3 and 2. 3 and 3. And then for the force vector, I'm just gonna do it. So n1 plus equal f0, f of n2 plus equal f1, and f of n3 plus equal. And that should be it. So now at this point, we should have the global stiffness matrix and the global force vector. And now we need to solve. So for solving, this one is not here, so you cannot look at the code here. But what I'm gonna do is I'm gonna stop sharing there. So I'll give you 5 minutes to do that. Because I'll tell you what you have to do. So at this point, we have the global K, we have the global F, and I forgot here, there should be the reactions, which we don't know. If you expand this, this is K, this is T. I'm gonna put minus F here. Minus the reaction. And so here what we need to know is that for the first 15 entries here, the first 15 nodes, we know the temperature. And then we don't know the reaction. So here there should be 15 reactions that we don't know, and then this just has zeros. So to solve the system, what we are gonna do is the same thing that you were doing for your homework 3, is we're gonna partition the system at that 15 mark. So that one you can go to your code from homework 3 and just set NE equals 15. And then this one will be the KE matrix. Is this 15 by 15? This one will be the KF matrix. This one will be the KEF matrix. This is KEF transpose. So you need to partition the system. Then this one right here is going to be the F. And then these ones are all zeros here. So that, and this one is TF, and this is TE. So the temperature at the nodes that don't have essential boundary is just going to be KF inverse times FF minus FF, and then minus KF times TE. Again, this is the same as in homework 3. So go ahead and set that up. Again, you have to partition your system. You can follow the homework 3 if you did it with the partitioning of the system. I'll give you maybe 3 minutes and then I'll just do it.
Should work.
Is that the solution? Is that the solution for this one?
Oh, no, that's well. It's not. So you have actual code that relative here.
I did that last time.
What was that?
Like, was this already?
Yeah, this is our.
Not really. No, I didn't say this.
Yeah, I don't think we're just looking at the chart. That's the temperature bottom. See that?
I mean, what's
Yeah, the source and the source.
oh, then it's not needed. I mean, I probably still do the partitioning. Yes. But you know, if the TE is 0, then that term goes away. But you still need to do the partitioning. All right. Stop sharing here. Share here. So hopefully you copied the code from class. It's not in this one. Thank you. All right, so I don't have it here, but well, I know this. So NE is just 15, and then I'm just gonna do this. You can copy from previous code. This is just 0 to NE, 0 to NE, then KEF is just NE to the end, and then 0 to NE, and then KF is just NE to the end, NE to the end. And then FF is just F NE to the end. And then we need to create the TE. TE is a vector of MP1s size 15. I'll just do NE. So this TE has the 15 nodes. We said we were going to set the temperature to 5 for those nodes. And so I think I have everything that I need. So TF, which is the temperature at the free nodes, is just solve KF and then minus FF minus the dot product between KF TE. This is exactly as it was for one of the previous labs. So that should have worked. And I'm out of time, but this is the solution. I just want to plot it. Just want to stack it, and then I don't have plots here, but I think I don't know if this will work, but let's see. It's not color. Does it work with TSO? I don't know how to set up the color here. Maybe I need tree contour. Well, we're out of time, but I'll just plot the solution. I just don't remember what is the correct argument here for. Maybe I need tree contour. Nope. Maybe like that. If only I remember. ChatGPT, where are you? Oh, there we go. There we go. Trial and error. Okay, so this is the solution. So tree contour, and then the T-sol just has to be at the end. All right. Hopefully that is what you got. And see you on Monday. They work. Yes, no. Work. Work. For that, work. Just shift. Shift and they just on myself. All right. Let's go.